In the last video, we talked about this sort of sponge-like property of cartilage, and in this video, I want to look at what the implications of that are for the mechanical properties of cartilage. So what would happen if you took a piece of cartilage from the back of the patella, for example, and you put it into a mechanical loading system, and you looked at its stress-strain curves as a function of the applied compressive force? Because, of course, cartilage, being between joints, is made to withstand two types of loading. Primarily compression, and also shear. So this is different, by the way, from tendons and ligaments, which were mostly withstanding tension, right? So it should be pretty obvious to see why cartilage experiences compression, right? It's because it's getting compressed between the joint surfaces. But what about shear? Well, suppose you have a joint surface like this, and another joint surface like this, and there's cartilage, here. Actually, there'd be cartilage on both sides, but let's ignore that for now. Obviously, if this bone was getting pushed in like this, there'd be compression. But what if the bone was getting pushed like this? Then this part of the cartilage would want to be going this way, and this part of the cartilage would want to be going this way. So you get cartilage shear as well. So that's something to be aware of, but what I really want to focus on in this video is what happens to the compressive strength of cartilage when you load it. Let's I said cartilage has this complex three-dimensional structure, which it does. And let's maybe continue with this example. Let's say, I don't know, maybe this could be the humerus, and this could be the shoulder joint. So maybe you've got some cartilage in your shoulder, and let's say we took like a little slice of it, and we expanded, looked close up at that slice of cartilage. What's interesting about cartilage, unlike tendon, well, I guess not that much unlike tendons and bones. Do you remember how as tendons insert into a bone, they sort of become more bone-like and they get more calcified? Well, cartilage kind of does the same thing. Down here at the bottom, meaning the surface that's closest to bone, the cartilage is really stiff and really calcified. And then as you move away, as you move into the joint space, it gets softer and squishier and more hydrated, meaning has a greater water content. And this plot that we're going to look at shows very nicely that behavior. So this study divided a piece of cartilage up into a bunch of different layers, going from deep, meaning right by the bone, to further out. And here's what it looks like. Suppose we did mechanical testing on a piece of deep cartilage like this. Its stress-strain curve would be like this. Notice, number one, it's really steep. So it's almost, it's very, very stiff, and it has no really discernible toe region. So it's almost like bone, right? It's almost like the stress-strain curve of bone. Very strong, very stiff. If you take a sample from kind of somewhere in the middle, like maybe here, you get something more intermediate. You get a little bit of a toe region, and then, I guess that's kind of hard to see, but you get the idea. You get something like this. And then if you take a sample from really right out near the surface, the kind of the bone on bone, or no, the cartilage on cartilage junction out here, it's much softer, much squishier. It's like this. So cartilage is, and I'm going to break out that big word from last week, cartilage is also anisotropic. It does not respond the same way in all directions of loading, and even inside the material itself, it has different material properties down here than it does up here. And in the case of arthritis, what happens is you are losing this cartilage surface. And so you get less and less cartilage, and the cartilage that you have left is harder and harder and harder and less springy. So from a joint health perspective, that's not so good. But broadly, this is the mechanical response of cartilage, and it's this very interesting, unique material that has different mechanical properties at different layers of depth into the cartilage itself.